Let me just remind you, I mean, we are thinking of point process. I mean, so we have points on the line or maybe in some interval. Let's say lambda. I mean, later on, actually, we will have also lines. I mean, so this is then actually on a two-dimensional space, but never mind. I mean, let's just concentrate on the example which I discussed yesterday. And so the point is that the definition is that, I mean, you know, for very particular type of point processes which are called determinantal, I could compute all the correlation functions in terms of a single kernel, which depends on two variables, and the formula which I've written is, you know, I've written down for you again. I mean, just to remind you. So that's the nth correlation function as a function of its arguments, which are all living in this space in which the points are lying, which is the interval lambda, let's say, and it's given in terms of this n-dimensional determinant, which is obtained by inserting the arguments which you see into that kernel. Okay, so this is the definition. And now I just want to sort of do two properties of these things, and that's it. I mean, so the first thing I want to sort of tell you what is the generating function. And I remind you that in the case of a Gaussian field, if I would try to integrate something like a dx, my field phi of x, and then maybe I have to smear this against some smooth function f, and then I do an average. In this case, I mean, we have a simple formula, right, which is integral of x of y. Let's see, dx dy integral f of y, x of y, and then here I would have put the correlation kernel c of x and y and f of y, right? I mean, so this is sort of. And so the question is, there something similar for these determinantal processes? And the assertion is yes, indeed there is. But of course, it's not the exponential function, it's some other function. And so the formula for the generating function is that I'm looking at the product of j equal 1 up to n of 1 plus, and now just like here, I mean, there's sort of some testing function, which is called g in this case, g of y of j. Okay, and so it's just a product, and yj are the points in my interval delta, and of course n is random because, you know, there could be 5, 10 arbitrary number of points in this interval. Okay, and the assertion is that this very particular thing I can compute in terms of a determinant, which is now no longer a finite dimensional determinant, but it's the determinant of this somewhat modified operator, and it can be written as 1 plus g, let's see, g times k. Okay, and this is sort of, you know, I mean, this is shorthand for the operator which has the kernel g of x, k of x comma y, right? And because of the determinant, you know, I can sort of circulate through. I could put here another g over here, but let me just write it like this. Okay, so now the question is a little bit, you know, what is what would be a determinant? I mean, you know, if this would be a symmetric operator, you could just write it as a product of the eigenvalues. But in this context, I mean, you know, there's a simple formula for this particular determinant, which is called the Fredholm determinant. So this is a Fredholm determinant. And let me just write this in general. I mean, so I have 1 plus a matrix A. I mean, you can think also, of course, the formula is also true if A would be simply a, you know, finite dimensional matrix, but it's in particular also true if it's sort of like an operator. And so it's an infinite sum, which is written like 0 up to infinity, and, you know, has the same flavor as what is sitting up here. It's the 1 over n factorial, and I have to do the integral over dx1 all the way up to dxn. Okay, and what I have to put in is sort of, you know, again, a determinant which is formed exactly like this. So it's a determinant of A of xi, xj, and this goes from I comma j equal 1 up to n. Okay, so these are formulas which you can verify, but that's a very useful thing. Now, why is this a useful thing? Because it allows us to do two computations very easily. So one thing is sort of somewhat surprising, actually. I mean, but it's a true fact. I mean, so, you know, if I think of this sort of my base space, well, let's say this was my lambda, is a part of the V line, and now I concentrate on the points which are lying in some a given interval, which is, let's say, I call this interval B, and B is just contained in the lambda, right? And now you could ask yourself, if I know that on the big space, on the big interval on lambda, I have a determinantal point process, what will be the distribution of the particles which are sitting in this interval? This is usually a very difficult question, because you see you're giving some formula on something for many particles in the big interval, and then actually looking at what the distribution is in the small interval is a complicated computation. I have to do this integration and everything. Here it turns out to be very simple, and the answer comes because for this generating function, I can basically just here the characteristic function of this interval, and then you see in this formula, this characteristic function will just mean that, here I integrated over lambda to the power n. I'm just integrating over, rather than over lambda over n, I just integrate over the interval b. And therefore, it must be, because, this is sort of, it must be just, this just means that all what I have to do is I have to modify the kernel. So this will be determinantal. And the kernel for this interval b is simply the characteristic function of this interval, and then I have to put the kernel in which is defined on the big interval, and then just to make it more symmetric, I write it like this. Okay, so I just have to restrict the given kernel, which defines the determinantal process, to the particular interval I'm actually looking at. So that's a very nice, unusual probability. And the other thing, which I discussed already, and then I told you already why this will be important if you want to understand these height fluctuations. There's a formula for the so-called Hall probability. So what is the question? Well, again, I have my big interval. So here I take my sub-interval, let's say, B, and I want to know what is the probability that there's no particle inside that interval. This is called the Hall probability. So when we discussed the eigenvalues of random matrices, there was sort of the question of what is the distance between neighboring intervals, and that's sort of related to this Hall probability. So in our case, you will see that the quantity of physical interest, is again a Hall probability. So what is the general formula? Well, it's not so easy to compute, so no point in B. And what you find, it's given again by Fredholm determinant. So I just remind you that this determinant, of course, are both determinants, but this is, of course, simply a finite dimensional, and this is an infinite dimensional determinant in general. And so here again, it will be an infinite dimensional determinant. And so it's simply, so psi b is the characteristic function of this interval. And then I have the given kernel. And I can put it on the other side. So let me do it. Okay. Now why is this true? Well, let me not do it. Let me just leave it like this. Okay. So now why is this true? Well, it's easy to figure out, because when you look at this characteristic function, and now I put here characteristic function. I put for G, I put the special case that this is minus the characteristic function of this interval. Then what I see here is simply the product of J going from 1 up to n, and that's 1 minus the characteristic function of this interval at the point yj. Okay. So these are the actual, these are the positions or the locations of the points. Okay. Okay, chi is the characteristic function, so psi b of x is equal to 1 if x is in B, and it's 0 or not. Okay? Okay. This one? Well, it's just what I mean. I take this kernel, and then whenever the argument is outside this interval, it's just 0, and whenever it's inside the interval, it's just 1. Okay, and it's the same thing over here. The chi p says that whenever I put the argument inside the interval, it's just what I said. It's the same function. Okay. All right. So let's see whether we can do this exercise. So you see that whenever I take one point inside the interval, then I will have at least one factor in this product where this is equal to 1 and 1 minus 1 is 0, and so this will be always 0. Now, if there's no point, I mean, then, you know, it's a product of ones, and so it's 1. So this is just sort of, you know, the function, you know, it's just a function of sort of the set function which characterizes this event. Okay, so you have this simple formula. All right. So now I have to come back to you know what we really want to study, namely so this is now chapter 8. I mean, this is PNG, and you know, before I said something about determinantal and then this line constructions, and so here I want to say now about the shape fluctuations. Now we have all the tools, and so we can discuss this. Okay, so we sort of worked a little bit last time, and we did this multi-layer construction, and the object on which I'm now living is sort of slightly more complicated. I mean, you know, this is here a discrete lattice, and here I will have my interval from minus t to t, and the objects of, if you wanted to sort of compute correlation functions or any other statistical properties, actually these lines. I mean, so maybe I just put 2 of them. So okay, so maybe one like this, and then we had going down here. Okay, here they were all flat. Okay, and then maybe there was one which was over. Well, okay, let's say another flat one, and then there's one which is going up. And okay, so this was this line ensemble which I tried to construct last time. Okay, and the temptation which we introduced was that I had an eta x of j. So x is this variable, and j was this variable, and so this was equal to 1 if there's a line, and 1 if there's no line, right? Okay, and now the claim was that this is a determinantal point process. Well, okay, I mean, you know, if of course I cannot go, you know, through the argument. I mean, this is a somewhat lengthy argument, but nevertheless, you know, I should tell you what is the kernel which comes out of this computation, right? I mean, so now I will give you the kernel. Now you see here I had the kernel which depends on x and y, which is sort of the underlying space, but now I have a kernel which depends on both variables. I mean, you know, the positional variable, also the x variable, continuous variable, and then the discrete variable j, in order to specify the two-dimensional field. And so let me write down the formula for the kernel. So this was determinantal, and the kernel which defines this thing. So that's of course the crucial part of this computation, because unless I know the kernel, of course I cannot do anything. I mean, but the point is I have to know the kernel. So first of all, the time was fixed. So there's a parameter which is t here, and then the kernel depends on x and j. So this is one argument. And well, instead of using x and y, let me just use prime. So the other argument of the kernels are x prime and j prime. Okay. And now I'm going to write down this kernel sort of in a way which is already useful for the asymptotic analysis. I mean, there are various ways to write this kernel, but I'm using sort of one particular form. And this is written like this. And now let's see. Maybe I should really have. Oops. Maybe I should have really given a little bit more space so you remember this picture. And so let me just sort of put this over here. Okay, so I have this kernel B of x comma j, and then the other argument is x prime and j prime. Okay, now I have to distinguish whether I have to distinguish a little bit, you know, whether these arguments, whether one is smaller than the other one, and so this is why I need a sort of a little bit more space here, and so I write it like this: it's e to the minus x delta. I will explain all the symbols in a second, but let me just write it down. So otherwise, I cannot explain. And so I have x prime delta, and this is a function of j and j prime. And this is the formula which is true if x prime is strictly less than x. And then there's another piece of the formula which is e to the minus x delta. It looks very similar. The only thing is that now I have a projection which is larger than 0, and here's an e to the x prime of delta, j prime. Okay, and that's the formula if x prime happens to be larger than x. Okay, so this is an explicitly computed kernel. Now the symbols I have to explain in a second, and so I do the following. So the delta is simply the nearest neighbor Laplacian. So let me just write this. So maybe I do it. Okay, so I do it like this. So first of all, the h of t is sort of just a sort of one-dimensional hopping matrix. So that's this operator which is sitting here. And the way I can write it is that I think of this acting on a wave function, if you want so. And it has sort of the usual form. I mean, so I have, I guess there's a minus sign in my convention. So there's a minus one, and then there is, let's see, what am I? Because I put the minus sign there. Okay, that's fine. So there's minus j, okay. And then there will be like a potential term, which is linear in j. It's like 1 over t, and it goes like j. Okay, so it's a tridiagonal matrix. I mean, the diagonal elements go like j over t, and then I have two off-diagonal elements which are both minus 1. And then there's, of course, the Laplacian of j, which is minus j. I guess in my notation, no, I guess I put the full thing. No, so the Laplacian is the usual one. I mean, so psi j plus 1. I mean, in the Hamiltonian, I put minus Laplacian. Here, I put the V Laplacian. So it would be minus psi j, and then there would be plus. All right, so we have this one. Okay. Okay, now let's see. So whether I defined all the symbols. So here you see the Laplacian. So is this you should think of. So this one you should think simply as a transition probability of a simple Van Walk. I mean, because this is just exactly the usual nearest neighbor hopping, and I need this term in order to preserve probability. All right. Now, what do we see here? Well, here we see the Hamiltonian of a particle. If you think quantum mechanically, I mean, we think of a Hamiltonian of a particle, which of course has the usual kinetic energy, the hopping terms to the right and to the left. But then the particle is actually sitting in a linear potential. But the potential, that's of the important T dependence. I mean, the potential will become very flat as I look for very, very long times. Okay? And now we have this sort of funny formula. Otherwise, I guess I have explained everything. No, I didn't explain to you what is the P. Okay? Now the P, okay, this is just a shorthand notation. So what should I say? Okay, so you see this is a linear operator, right? I mean, so it's this linear operator which is written explicitly over here, and my notation is that p less or equal to 0 is equal to the projection onto all states with eigenvalues less or equal to 0. So in the usual Dirac notation, I mean, this object would be the sum over, I don't know, eigenvalues lambda j, which are less or equal to 0, and then I here would have the eigenvector, which looks like this, right? Okay, it's just the same thing. All right, now sorry, but this is just sort of what the formula is, and now we have to look a little bit at this operator, and let's see. Now, first I want to do one. Okay, now actually I should tell you a little bit about this operator. I mean, so this operator actually can be diagonalized in terms of Bessel functions, and the eigenvalues of ht are actually equally spaced, and they are of the type m over t, and m is in c. You see, it's unbounded because I have a linear potential, and so I will have eigenvalues of arbitrary negative energy, but it so happens that despite the fact that in this for the linear potential, so happens that the eigenvalues are equally spaced. Okay. And the eigenvectors are the Bessel functions, which I'm not going to use very much at all. Okay? Yes.
somewhere. So the Laplacian is next to the. So there was a claim that there are these independent self-avoiding random walks, and Laplacian responds to random walks apparently. But then what's HT with this potential? So like.
Okay, you see, okay, the question is where does the potential come from? I mean, so I can, of course, it comes from the computation. I can also give you sort of like a sort of more physical argument. I mean, basically, I mean, when you look at the picture which I showed you, I mean, which were these lines. I mean, then there seems to be sort of like a force. I mean, the lines were going sort of roughly up to a semicircle, and then above this I saw no lines at all. Now this basically comes from this potential. You see, I have particles sitting in a linear potential. Okay, and this linear potential, it's a potential which looks like this. So this is this is the V, and this is the J, right? And the slope, the slope is 1/t. And so basically what this formula is telling you is that, so let me make a slightly better picture of this. So I have to go back to my standard picture. Well, this I will go anyway. When I want to look, let's say, in the middle, right? I mean, so I look at this thing here. And now what I see is that now I look at the eta, at the field at x equal to 0 as a function of j. So of course there I will just see points. I will see points here, and then I will see more points down here. But eventually I said, all the lines are filled. I mean, so here I will have just sort of particles being sort of, as closely spaced as they possibly could be. And up here, at some point there will be a last particle and there's nothing above it. And this basically it corresponds to, fermions at 0 temperature sitting in a linear potential, right? I mean, so they are sitting in linear potential. I mean, these particles, they all would like to sit at minus infinity, basically. But you have the Fermi repulsion, and therefore, the only thing what you can do, and this is really physical space, so to speak. I mean, so all what they can do is they basically sort of. I mean, they come as close as they can possibly do, and that's just sort of defined by the underlying lattice, right? Okay, and then here there's some dilute region where they do, have more freedom, but then finally they see this linear potential, which is sort of, confining them, and then eventually, it will be energetically totally unfavorable when they will not go beyond a certain maximum. There will be a last particle, it's sort of like particles sitting in a sort of linear gravitational potential. There will be a last particle somewhere, right? So this is what's actually happening, and yes. Okay, so maybe so now I want to use this little formula here, so that you can see what is the quantity which I actually have to investigate. And what you see is that so let's I mean, just what I said over here. Let's take x equal to 0. Okay, and now I want to look at my P&G height. This was sort of the top line. So I want to look at my P&G height at the point x at time t, right? I mean, this is after all what we wanted to compute. Okay, and now let's look at the probability that this is less or equal to n. Now you see that if the height has to be below level n, I mean that above level n, I mean there cannot be anything. So this means simply the probability that that the eta, let's see, I mean now we are looking at 0, that the eta of j is equal to 0 for all j greater than n. Okay, and you see this is a whole probability. So what I'm saying is that if I want to look at the distribution function of the height, this amounts to actually computing what is the probability of finding no particle above the level n. That's the formula which comes from this determinantal structure. Now this, of course, I can now write down, and so let me do it. Let me see. Actually, I'm not totally sure whether I really want to do that. Just a moment. I have to look at my notes. hmm I had to restructure a little bit by my notes. Okay, so yeah, this is what I want to do now. Okay, you see, so now I'm looking at x equal to 0. So now you see that I actually looking at this particular case, both x and x are equal to 0. So I only have this projection sitting over here, and so you see what I have to compute is this is equal to be the determinant of 1 minus. Now I have to project from n up to from j larger than n. I mean, so this is j. Well, okay. This is a characteristic function of the interval n plus 1 to infinity, and then the kernel which I have to plug in is this kernel which comes from this Bessel operator, which is a projection onto all the eigenvalues which are less than 0. So this let me call this like this. Okay. So now you see I have now an explicit function. I have an explicit expression for the object which I'm really interested in. I mean, finally I get a formula for the distribution of the height. Now, because of the construction, it's not a totally trivial formula, because you see, I mean, I have first this kernel which at the moment, I would have to write down all the eigenvalues and all these things. I mean, but in principle, you can imagine that there is a sort of fairly explicit formula, because the eigenfunctions are very explicit. There's a rather explicit formula for this particular projection operator, but then I have to sort of project it onto the interval from n all the way to infinity. Sorry, this should be infinity. Okay, and well, okay. So now we as you see, I mean, I don't know whether you remember. I mean, what the general scheme was, but the general scheme was that I have to do some non-trivial identity, and eventually, I get sort of like, in this case, if you want so directly, but some sort of generating function for the object which I'm really interested in here. So I get a simple function for this, simple formula for this distribution function, but it's still sufficiently complicated that I cannot simply read off what the asymptotics is. Okay. Now, if you want to do the asymptotics of these things, I mean, again, it sort of requires a little bit of more thinking. I would need some nicer formulas for this projection, and so I simply want to avoid this completely, and I want to explain you a shortcut which I find very, very sort of useful. And the point is that this shortcut actually works in many cases. I mean, it also works if you want to get a Tracy rhythm distribution for GUE random matrices. It works for all the ensembles. I mean, this unitarily invariant ensembles, which Sacha was to explain you. I mean, from this formula you can see immediately why whenever you look at edge statistics of random matrices, it always should be given by the Tracy rhythm distribution, independent of what particular potential actually I'm using. Okay, so let me just show you the shortcut, which is quite simple. So I have to write down again. Okay, so you see, let me see whether we can sort of see what I have to do. I mean, so here somewhere 0. Now I know already that the maximal eigenvalue will be typically around 2t. I mean, that was sort of the macroscopic equation. And so what I really have to look at, the point 2t. So this is my j-axis, and I have to look sort of at these points close to the interval. I mean, this is sort of where the interesting behavior will be. And so what I will do is I want to concentrate on j, which are at the point 2t. I mean, that's sort of the edge. I mean, this is sort of beyond 2t, it's very unlikely to find any points at all, but it's near 2t where I see an interesting crossover from this completely filled thing. And then we somehow know already, because I discussed at length that we sort of expect KPC type of behavior, that we should look at the distance of order t to the 1/3. And since we don't know exactly, I say distance, I mean, we have to put some scale, and so let me put a y, and of course the y is sort of considered to be of order 1, right? I mean, so I'm going to look now at points which are close to 2t, but they are distance t to the 1/3 apart. So that's exactly like the edge statistics for random matrices. You know, I'm at the edge of the Wigner semicircle law, and then now I want to investigate more closely what happens actually very near to the semicircle law. Well, I mean, you know, that's not so hard. I mean, you know, I have written down for you this very explicit operator, and so why don't I just sort of transform this operator by you know, just considering things which are close to this point. I mean, just sort of do a rescaling in terms of you know, in terms of the J, and simply plug this into this equation. So why don't I do this? I mean, so let me call this h tilde of t. So this is now transformed to these new variables, and of course it's not so hard to see. I mean, so so this is acting on a psi, and this depends on y. You know, others are just sort of parameters. And what does it look like? Well, you know, it's minus. So y is the deviation from 2t. I mean, so now I have to go one to the left and one to the right. So it's minus psi of y. Now the y is j times t to the minus 1/3. So there will be so there will be, because I go 1 unit. I mean, I must go minus 1/3 on the y scale, right? That's just j equal to 1. Well, then there will be the other term, which is psi of y minus t to the minus 1/3. And then there will be the linear term, so that's t. And now I have to plug in my j, so this is 2t plus t to the 1/3. Okay, so this is just my rescaled operator, right? So this means one lattice to the right, one lattice unit to the left, and this is just the potential at the edge. I mean, the potential at the point 2t. This is times y. Okay, it's a linear potential. Well, so this is easy. I mean, now you just do the second order expansion, right? I mean, you see that when you look at the lowest order term, I mean, you just get exactly the okay. So there's a 2t, there's a 2 times pi j. So this altogether will give you exactly the second derivative. Yes. I'm looking at an operator, and I want to know what this operator is acting near the edge. This is what I'm doing, and this is what the transformation. Of course, a priori I can do any sort of linear transformation over here, right? I mean, but I want to concentrate on the edge. Psi of y. That's what I've written. Psi y at you know, a little bit to the left and a little bit to the right, and here is a multiplication. Psi is a function of y. It's a wave function if you want so, right? No? No, is that fine or not yet? Well, I give you some function psi, and I ask you to compute h tilde of psi of y. I mean, h tilde acting on psi as a function of y. Well, so what I have to do, I have to take this function and I have to shift it a little bit to the right with t to the minus 1/3. With a minus sign, I take the same function, I shift it a little bit to the right. Okay, and then I take the same function, I multiply this with this, and then I add 3 terms. That's the resulting function.
Yeah, the expression for j is weird for me then, because you have y multiplying t to 1/3, and you have y minus t to 1/3, and this is
It's just shifting the function by t to the 1/3. Because that's what it was over here, was j times pi j. I'm not sure what. No, still problems. Okay, all right. So now it's obvious. You know, I assume that psi is a smooth function. So we do a Taylor expansion, and so what I find is that I get altogether t to the minus 2/3 because I do second order Taylor expansion. So here I have a minus sign already, so I get minus the second derivative. So that's the second derivative vector psi, and then I get simply plus y. You see, it just works out because, this term is like t to the minus 2/3. So this is what I pushed in front, and the 2t goes into the Laplacian, right? So it's 2t divided by t, which is 2. I mean, so this goes into the Laplacian, and so you get y times psi of y. Okay, so I get, the quantum mechanical, the Hamiltonian of a particle now in the continuum sitting in a linear potential. Is that fine? Now this operator, to have a name, is usually called the Airy operator. Okay, it's just a name. I mean, so because the eigenfunctions of this, so the spectrum is I mean, the spectrum of this operator is R, and the eigenfunctions. I mean, for each eigen, they are the standard Airy functions, let's say of x minus lambda. So they're just displays Airy functions, and lambda is the corresponding eigenvalue, right? I mean, so this is what it is. Okay. All right. Okay. So now, but you see, it's a little bit more complicated because I don't want. Of course, I'm very happy about this operator, but I really would like to do the projection onto all eigenvalues which are less or equal to 0. Well, okay. I mean, now of course you have to worry a little bit, but I mean, let's assume that things work nicely, and so somehow it's less than 0. So somehow this limit pushes through, and so eventually what this will go to is simply the projection onto all eigenfunctions of this operator, which are less or equal to 0. But this, of course, I can now easily write. So the projection of let me call this operator H Airy of H Airy less or equal to 0. Well, it's just the integral. It's just exactly that. I raised this formula. Well, then I have it again. I mean, so it's an integral from minus infinity to 0, because those are the eigenvalues. I integrate over all the eigenvalues. Now, of course, you have to worry about normalization. You're working in the continuum, so in principle, you should worry about how that these Airy functions are properly normalized. But it so happens that I put already the correctly normalized eigenfunction sitting over here, right? I mean, that's sort of that's the way how the Airy functions are defined. I mean, people realize that to make a sensible definition, you want to have it in such a way that you have this sort of inner product sort of defined. That okay. So now you see that okay. So now I've confused you, but let me write this again. I mean, so I have this Airy H Airy less than 0. So this is an operator, but now I think of this as a kernel. So if I want to use the Dirac notation, I will do this thing, and I will do this thing. So now I have this as a kernel, and this integral kernel I can write explicitly in terms of the eigenfunctions, and since it's less than 0, I integrate over all eigenfunctions from minus infinity to 0, and now I have sort of okay. And no surprise, I mean, this kernel is called the Airy kernel. Okay. So now we are done. Why are we done? Yes? That's the eigenvalue. It's just the eigenvalue. Every point, I mean, this operator at every real point will have an eigenfunction, and the eigenfunction is given by this Airy function. So this is just the integral. And as I said, I mean, there's a normalizing factor. You have to normalize these eigenfunctions, but they are properly normalized. All right. So now we are done already, because what is the conclusion? Well, the conclusion is that if I so let me write down what the conclusion is. So this is now the P&G model, right? So I look at the probability of h, so this is the height, my P&G height at the origin. Now you see, I shift it to t. I mean, this we know already. So I put here 2t. That's the 2t which appears here. And now I have a deviation of order y to the y to the 1/3. Okay, so you see already that the fluctuations of this h is of order t to the 1/3. Well, and the assertion is that if I take the limit as t to infinity. So this is what I have done. I will find actually that it's given, of course, again by this whole probability, but now for the limiting operator. So you see, I mean, this one sort of goes over to the area kernel, and here, of course, I have to put in the correct interval, which is sort of this interval, but now v scaled. So what is left over is sort of just the y of this interval. Okay, so what I have to do is I have to compute the determinant of the following thing: 1 minus. Now here comes the k-arid kernel, so that's explicitly this quantity here. Okay, and now I have to do, I have to compute the whole probability. I mean, I need the dependence on y. So now the whole means that everything above y should be empty. So this means that I have here a projection of y all the way to infinity. And let me just, for symmetry, let me put it, I mean, just to emphasize that this is actually a symmetric operator. Okay. So this projection means that it's just like with 6IP. I mean, it just means that I take this kernel and I only, I put whenever each, any one of the arguments in the kernel are outside the interval, I just put it equal to 0, right? Okay, so this is the famous Tracy-Witten distribution for, distribution for the largest eigenvalue of GUE matrices. Okay, so exactly the one. Well, I mean, Sasha had no time to discuss it yet, but I mean, he sort of at the very end of his lectures, I mean, he mumbled something, and he argued, what how close are the eigenvalues at the edge. I mean, I'm using here a somewhat different scale. I mean, in my case, I mean, the height is sort of. The particles have a minimal distance, so there cannot be 1/n. I mean, the particles have distance n. The edge, if I do the analogy to what Sasha was explaining, so if all these eigenvalues, so in my case, I mean, this distance is actually order 1 because the height just goes in units of 1, and then this will be of order 2n. And then the fluctuations are of order n to the 1/3. That's exactly what he was telling you an hour ago. Okay, and so, and if you would, if you use his formalism, and of course you can do something similar, I mean, you would end up exactly with the same limit. Okay, so there's one bonus at that stage, namely that you see that by the somewhat heuristic argument, as you sort of follow this all the way up to here, you see that I also find the correct time scale, which is t to the minus 2/3, right? I mean, so the fluctuations, if I start looking sidewards, I mean, so let me tell you about the t to the 2/3 again. So this sort of, so the t is the lateral direction, right? I mean, so when I I mean, here is my my P-and-sheet droplet with some fluctuations. So what we just studied was just the statistics at x equal to 0, and there I found that they go like t to the 1/3. But then if I would ask along this direction, how are things correlated? Think of this two-dimensional picture. Then here I looked at this one. Now I want to look at correlations in this direction. That's of course exactly sort of what corresponds to this t argument, and therefore here you will find correlations of order t to the 2/3. Okay. So this, okay, so I have to sort of, well, because you see things, I mean, the t, I mean, which I'm doing here is sort of telling you what is, okay. You see, the t corresponds to a transfer matrix which sort of is acting in this direction. So the question is, how many units do I have to go in terms of this transfer matrix in order to see something which is sort of order 1? And since I here have something like t to the minus 2/3 sitting, if I go a distance t to the 2/3 away from the origin, then I will see some non-trivial correlation, right? Yes? Okay. Yes. No, no. What is the question? I mean,
So I'm just wondering what's the order of derivations. So first we derive
where you're looking? Which picture are you looking at?
J is 2t plus y.
Yes, that's right. Yeah.
That's an anything guess that later.
Well, I argued so many times, and first of all, the 2t I computed for you because I told you what is the macroscopic shape, right? I mean, so I computed for you that. I really computed for you that the macroscopic shape is at the origin. If this happens to be 2t, I mean, then it will be also 2t away from the origin, right? I mean, so this I know. This I know from. Okay, so this I know from the macroscopic. Let's see. So this I know already from my macroscopic computation. Now here, of course, I could have put in some first of all some arbitrary power, right? I mean, I could whatever you put some gamma, let's say. Now, of course, you can go through the same computation. You ask yourself, how would I fix the gamma? Well, I fix the gamma by getting some finite limit. Then, of course, you find it must be t to the 1/3, right? I mean, so. Yeah, sure. No. So, yeah. Of course, can I also see from this equation that I should put this at 2t, right? Otherwise, you will have no limit, right? I mean, I'm looking at this operator, you get all the information. I mean, you don't really have to assume anything before. I mean, basically what you want to say is that, after doing, let's say, a rescaling of this type, I mean, you want to make sure that you get a finite limit, and then all the things are actually fixed. I mean, non-zero limit, yeah? Okay, so now I have to sort of go a little bit. I mean, there are many other things which one could say here, but I want to use sort of the second part of that first hour to tell you that one can do. So this is now sort of really more telling the story rather than giving you details. I mean, I think this is something very useful to understand because it's after doing quite some terms, I mean, we arrive something where we can actually sort of really do something fairly explicit. So now the next thing I want to tell you is that one can do something similar for the KPC equation. So this is now KPC equation. Now, the point of this chapter is basically to tell you what the result is. I mean, the methods to actually do this are more complicated than what I've been telling you here, and I just simply cannot say much about them. But I think the result by itself might be useful to understand. So let me look at our equation again. I think I put the 1/2, and then I have then the 1/2 dx h. And then I have my white noise, which I called psi. Okay. And now you see, this is what we learned from doing the PNG model, and what we learned from Johansson. There seems to be one particular initial condition where somehow the computations become easy, and the same thing is true for the KPC equation. And what is easy? Well, I mean, we sort of wanted to have sort of this kind of droplet geometry, which here was sort of imposed by, here for the PNG was imposed by having this ground layer. And so the way how you impose this for the KPC equation is that you do a sharp wedge. And so you assume that the h of delta of x of 0 is actually minus, the needle is upwards minus x1 over delta. And you want to make this sort of infinitely sharp. So I want to eventually let delta go to 0. So it's a very, very sharp wedge, right? I mean, it's sort of delta. And now you might ask, why don't I do another way of doing it? I mean, but there's a special reason of doing it in this particular way. And in fact, if you look at it correctly, I mean, there should be also sort of a diverging normalization. But let me not go into this. I mean, so this is what I take as my initial condition. And then, of course, I can ask the same thing. Namely, what I can ask is, can I say anything about the height times 0 already, with this correct normalization in the limit as delta goes to 0. Okay, and the answer is for that very particular initial condition, and for no other ones. Well, for some other ones, but I mean, really for that very special initial condition. I mean, there's something which we can say, right? And so first of all, there's the shift down. So the solution I mean, I had this already, but let me just remind you. I mean, so we have sort of initially sort of basically this needle here, and then the solution will look something like this. So it will be shifted down, and then we'll have fluctuation. So there will be this 1/24 times t. Okay, and now I sort of want to look already on the scale t to the 1/3. So I look at t to the 1/3. Let's see, what do I want to do? Yeah, okay. So I want to put this already in my formula, and then I have a parameter s. So s is sort of, again, it's so, I mean, this is the size, and that's the deviation from the linear term. Okay, and it's just an abbreviation. I mean, this. So I have another eta. I mean, so anyway. So this is an ET of eta of s, right? I mean, it's just a definition, okay? Okay, now the assertion is that for that very particular thing, I have a generating function. And again, I mean, the generating function. I mean, in which way this generating function is written is sort of not just comes out of the computation. I mean, it's not something which we anticipated before, but I have to look at e to the minus e times the eta of t, eta sub t is a function of s. And now I do the average over the white noise. So s is just a parameter which tells you what is the deviation from the linear part, right? No, it's actually shifting down. So then it will, no, there's nothing deep behind it. I mean, it's I mean, because we yeah. No, it's I mean, it depends on the situation. I mean, you can either shift up and down, and so I mean, since I haven't even told you how exactly the solution is defined, I mean, it's a little bit unintuitive. I mean, I completely agree, but sort of this comes out of it. Yeah, but only very short. I mean, after a while, I mean, if you think about it, I mean, this is really the solution of the KPC. Of course, if you think physically, I mean, the bulk would be down here, right? I mean, what? Where does it come from? Okay, I can give you an answer where it comes from. I indicated already, because you see, I said that we can compute moments for so. What last time I defined c like e to the h, right? And I told you that for these exponential functions I can actually compute successively moments. Now the moments of this thing, they're actually given by the attractive delta Bose gas. And so if I just want to have the leading term, what I basically have to know is sort of what is the ground state energy of the delta Bose gas. That sort of gives me sort of the leading term of this partition function. Okay, and now you look up in the books what people have written, and you look about the n-dependence. I have to do this for every number of particles, and you look at the n-dependence of you look at the n-dependence of the ground state energy, and then you find that there's you find exactly this linear term here with the 1/24. So I mean, 1/24 comes out of some computation, right? But it's really related to the delta. I mean, if you want to ask, can you briefly tell me, how I will do it? This is sort of certainly the correct answer. Yeah. Yes. No, it's no nucleation. Yeah, well, outside the light cone there was nothing. Yeah. Inside the light cone I have a lot of noise, right? So inside the nucleation events were inside the light cone, right?
So you do no similar suppression?
No. I just decided to look at this equation. I mean, there's nothing. I never suppress anything. I just sort of write down an honest equation and then I study it. Okay. Okay. Now the assertion is that this somewhat weird-looking quantity. So it's the exponential to the minus the exponential of this quantity, right? Now this, it happens that this quantity can be written again, and it's no surprise because you see I had an exact formula over here, and finally I found that the height actually can be written in terms of such a Fredholm determinant. Now here it's also the height, but it's some other function of the height. I mean, it's just sort of this Gumpel type thing. Anyway, so this can be written as a Fredholm determinant, and so now S goes from 0 up to infinity. Then there's a kernel, which of course is not the Airy kernel. You see, I mean, you should look at this formula. Here I had the Airy kernel, and what is Y over here I call now S. I mean, just to distinguish, we're looking at two different cases. So here I have a kernel which still depends on time, and this is a formula for any time t. And then there's again this projection from S all the way up to infinity. Okay. So again, it's an infinite dimensional determinant. I mean, that's the kernel of X and of on the real line, and then these are these projections. So it's sort of similar of this type. So the question is, what is K of t? And the K of t unfortunately comes out in a very simple way. Maybe Sasha is going to say more about this thing. So I just really want to display the formula and draw a conclusion. And the thing which you find is that so that's the last thing which I'm going to say on this x y is given. Well, I guess I used x and x prime. So let me maybe use also. Well, okay. Anyway, so let me use x and x prime. So it's an integral over du. Okay, so now there is sort of a slightly different convention. Here I put a minus sign because I'm integrating over negative values. I mean, here it's sort of usual to write over positive things. Okay, so that's the exact formula. This is integrated over all R. Okay, and now what you see that in the limit as t goes to infinity, the kt, because this just comes to the characteristic function. Now of the positive half line, because but then I put a plus here, so I can also convert this to the negative half line, and this will just go to the k area. And so from this we conclude that also for the KPC, height has tracy rhythm fluctuations. And so you see that I take two models which really look quite differently, and I have a sort of discrete P and G model, and I have this continuum continuum model of a growth of a height. And they both have exactly the same asymptotic distribution. Okay, so this agrees. Okay, so this is what we call universality. In two different models, I find the same asymptotics. And the other remark is that this equation by itself, of course, is not yet asymptotic. You see, I mean, you have an explicit kernel. You only get it if you really take the long-time limit. Okay, so I stop here, and we do something else after the break. So it will continue with random tilings. Okay, so that looks like a totally different chapter. I mean, it is a different chapter. And I was hoping that, I would have spent my time sort of more economically. I actually was planning to do the full 2 hours on random tilings, but, as it goes, I mean, you want to do some explanations, and then, so I will be fairly descriptive, but I think it is important that you understand that, there's sort of a side branch which came out of this KPC, which initially, I mean, nobody actually anticipated. And so I want to explain you a little bit what the connections are. And I thought that one way to do this is I will talk a little bit about the six-vertex model and maybe, if time permits, maybe I can say a little bit about crystal shapes. Okay. All right. So let's say we want to do the six-vertex model, and let me think of this as a problem of tiling of the plane. Then you have tiles, and in fact you have 6 tiles. I mean, so maybe this is why it's called six-vertex model. So there will be no errors in my, you usually presumably 1, 2, 3, 4, 5, 6, and 5, 6. Yes, okay, okay. And the way I want to do this, I mean, so this tile is just I mean, there's nothing. It's just empty. But then on the second tile, I will do this type of pattern. And I mean, you could cut it either this way or this way, but this is sort of, for what I'm doing, sort of the more convenient way. Then there could be just a line which is going this way. There could be a line which is going this way. And then I have the corners, and this is this way, and this is the upper way, right? Okay, and then since we want to do statistical mechanics, so this is equilibrium statistical mechanics. So we want to do equilibrium, and I want to give them weights, which I call. I mean, there are various conventions. I'm choosing as one of the standard conventions here, omega 6. Okay, and then I have a domain, let's say, and the goal is to tile that given domain, for instance, such kind of a square with these elementary tiles. Okay. Now, of course, you can do this it's completely random, but there's one constraint such that lines end only at, so if this is my domain here, lambda at the boundary at d lambda. Okay, so it just says that of course, somewhere they might end, but particularly if it's a finite volume, they have to end somewhere. But the point is that inside the volume, you just have to keep going. And so that, of course, poses you an enormous constraint of how to do the tiling. But that's sort of the statistical mechanics problem, right? I mean, you just and now you the only thing which I still have to tell you what is the weight of imagine that you have found sort of one admissible height, where the lines never end. Then I have to tell you what is the weight. Well, the weight is sort of the obvious one, weight of tiling. Well, the weight of the tiling is, you have all these tiles. I mean, you take the product over all tiles, and then you simply, so you take just a product of the Boltzmann weights, right? I mean, so this means that I'm summing over the whole bulk, right? And then each one has a little omega, and you just multiply all this omega together, and this gives you the weight of the tiling. Is that fair enough? All right. Okay, now I want to do some very particular boundary condition, which is domain wall boundary condition. So this is not a lecture on six vertex models. I mean, I'm far from being an expert, and but I want to sort of tell you why KPC is actually, and how KPC is actually connected, somewhat unexpectedly, but it is connected to such kind of tiling problems. Okay, so let's do the domain wall boundary condition. Well, that's easy in this language. I mean, all what I do is I assume that I have incoming. Well, you see, these lines have no direction. So when I talk about incoming, it's just sort of a language thing. I mean, it's they're just, I mean, as I have drawn. I mean, they're not. They have no orientation here. What is? The J, well, the J runs, I have all these tiles, right? And so this is 1, 2, 3, 4, over all tiles which are in my tilings. No, sorry, now I understand. This is stupid. Yeah. No. Okay, so it's stupid. I mean, so this is alpha of J, right? I mean, so, okay, yes. Thank you, yeah. Okay, now let's see. And the alpha, of course, goes, I mean, from 1 up to 6. Thank you, yeah. Okay, so now let's see. So now we do this domain wall, and here, I also have these lines, and the two other things are empty. And now I want to study this particular problem, right? I mean, so, I can do other things, but I mean, this is what I want to do. Okay. Now, of course, you might have a guess what's happening, possibly could be happening, maybe something more complicated one, but one sort of simple picture is that you say, aha, I mean, there's this is a big constraint somehow, right? I mean, now maybe somehow a line which is here, must somewhere end up somewhere over here, and then so for instance, it would be very stupid to take a line which sort of goes all the way up to here, because it will never sort of be able to satisfy the other boundary condition. And so one possible solution, that's not the only one, but I mean one possible solution which sort of I want to anticipate over here is that maybe it looks something like this. So down here I put the tile number 2, because that's easy to satisfy. I mean, so here I will have a regular pattern of tile 2, and well, here I just keep going. I mean, that's fine. So this will give me the pattern of type 3, where here everything is empty. I mean, so I put just the 1. And here I will just do the opposite, right? I mean, this looks not such a, what was this was for, right? I mean, this doesn't look like such a thing. And now in between, of course, I mean, since it's statistical, I will still a lot of freedom. So presumably, in the middle, I will see something which is disordered. Of course, that's a guess, and actually, it sort of is a little bit more complicated. You will see that it's not too far from the truth. Now, there's one thing which I wanted to, before going further, I want to explain one thing which is useful, is that the free energy of this model, right? I mean, the free energy is sort of the obvious thing. I mean, now I don't do it with domain wall boundary condition. I put periodic boundary conditions, and I compute the partition function and the log of the partition function. I take the volume to infinity. The free energy. I can do the same thing actually for this one. The free energy depends on the boundary condition. So, for instance, the free energy of the domain wall boundary condition is actually different from the free energy which I would compute with periodic boundary conditions. And this surprise, and I just want to tell you that it's not a surprise, and it's easy to understand if you have sort of the correct picture. You see, if you think about errors and plus and minuses, I mean, you might be tempted to think that this domain wall, that the 6 vertex model is sort of, something which is sort of similar to an icing model, only a little bit more complicated. And then, of course, for an icing model, I mean, this would be very hard to understand, why things would be so sensitive to boundary conditions. But the way to think about it is that actually, it's a model of an elastic membrane, or soap bubble, if you want so. And if you think about this physics, I mean, then actually it's not so hard to understand. And the way how this works is that, so here, let's do this for domain wall boundary conditions. I can do this for other ones. So maybe you have some lines here. I mean, so doing this somewhat schematic, and now you sort of introduce a height function. So this h is also a height function, but it has nothing to do with the KPC height function, right? And it's just a height function. And the way how I want to do this is that I mean, sort of some arbitrary convention, but I could call this sort of level 0, right? I mean, think of this sort of like a little mountain. I could call this level 0, and then this would be level 1, this would be level 2, and this would be level 3, etc. Right? And it's clear that because I have this condition that the lines should never end, is that I can think of these lines just as the height lines on my map, right? Okay. So you see, if I do an icing model, I could never draw such a picture. But here, because I have these lines which never end, I mean, this picture is sort of certainly correct. And now you see that this is this membrane, and now of course it can do sort of fluctuations. This height function is sort of like a sheet over this square base, and of course it can fluctuate. But it's really the height function which fluctuates. But now, it's sort of like elastic because, the height function is somehow coupled to its neighbor. And if you think about the height function, in terms of the height function, imagine that I put periodic boundary condition, then somehow, you would identify the heights on either side, and then of course, it sort of looks like a membrane with which, roughly on the boundary, or maybe I can take zero boundary condition, then, it would look like a membrane which is sort of basically, where the edge is sort of pinned. Whereas here, if I do it like this, I mean, and you see the height here, out here it's zero, but here it goes 1, 2, 3, 4, 5, and since if I look at this picture, somehow it's clear that I mean, if this is side n, and here is the height 0, I mean, then here typically, this thing in between will roughly be of height n. And so this means that now I have this soap bubble. Now I put a macroscopic boundary condition which sort of, tries to tilt this somewhat, or maybe in this way. And now, of course, what this soap bubble, now it's an elastic, it's sort of like a soap film, which is sort of, in this macroscopic frame. And now what this exactly will do, I mean, that, of course, now I have to understand in more detail what the statistical mechanics. But it's obvious that, if I want to compute now the surface free energy, that if I put it in a frame which is of macroscopically different from the periodic boundary conditions, I will also find a different free energy. Okay, so now let's see what I want to do is So now I mean let's assume for a second that it's sort of something like this here, and then you see, I mean, you say, okay, now this picture I've seen already in the previous lectures. It was sort of maybe sort of a little bit simpler, but it was also, I mean, if you remember the PNG, then down here it was perfectly ordered. I mean, here was sort of completely empty. It looks a little bit like this one here, right? So I mean, and then this is sort of like similar, kind of maybe also lines. I mean, I had also non-intersecting lines here. I have also non-intersecting lines. So why don't we make a guess that if I would look at one of these boundaries, this will be KPC like. So what would this mean? This would mean that first of all, there must be a macroscopic shape. I mean, just like in that case. Secondly, there is there will be shape fluctuations, and the shape fluctuations will have t to the 1/3. I mean, this distance to the 1/3 in one direction and 2/3 in the other direction. Okay. So this is of course the guess. Now the question is, can we support this guess? Yes. You take the log of the partition function. What else do you want to do? I told you what the partition function is. You see, I gave you the weight of a single tiling, and now you simply sum over all tilings which satisfy the boundary conditions with that weight. No, I have a question. No, I am answering or not?
So basically we have the weight.
Yeah. So for each configuration, I have my Boltzmann weight.
Yeah, right.
Well, and then I just sum over all possible. Yeah, exactly. Yeah. Yes. Well, that I cannot answer now. I mean, okay. Is there any other question? Yes. No. I mean, it's I mean, of course there is, but I mean, I cannot answer so quickly. Yeah. No. I mean, sort of. I mean, the weights. I mean, if the weights physically, sort of. Translate into the fact that in an elastic membrane, neighboring elements would have some interaction, right? I mean, some elastic energy. Now here it's sort of a little bit different, but it's sort of more or less the same thing. Yeah, it's a particular model. I mean, I'm not saying that it's sort of. Okay. Anyway, so now, okay. So the guess. I mean, I emphasize that the guess does not come on the level of the KPC equation. I mean, that of course, is very far from this. But once we understood. It doesn't come from the PNG model because even there I cannot see any tiles. But once I do this line construction, then of course in this picture I do see the lines, and then at that level we can actually make this kind of guess. Right? We cannot do it directly on the KPC equation. But if you admit sort of, if you know about the solution of the PNG, then this guess is actually not so unnatural. And in fact. There is what is no surprise, but nevertheless, I mean, it's still sort of important to note there is a special point in the phase diagram where the line ensemble, so that's this line ensemble over here, right? I mean, with domain wall bind, the line ensemble is determinantal. Okay. So we have again this magic situation is that if I sort of, do the parameters somewhat carefully, and I have to do a little bit more thinking, but in any case, I mean, then I get something which is determinantal, and when you actually do the asymptotic analysis, you actually verify this guess over here for that very particular point in the phase diagram. And so let me tell you, let me explain you this just a little bit more, because otherwise it's sort of, just standing sort of in the middle of nowhere. So let's first think a little bit how one has to do this. So what is the special point? And I want to give you a little bit of an indication what object is actually determinantal. And so let's see. So these are my tiles. Now, what you have to do is you have to, so the first one doesn't change, but this one is sort of redrawn a little bit. I mean, so actually I redraw this one like this. And yeah, this doesn't change. This doesn't change either. This doesn't change either. So 1, 2, 3, 4, 5. What did I do? No, this is changing. So I put this. Well, it doesn't really change, but I put it like this, and then I put it like this. Okay. Okay. And now the special. I need 7. That's the point. Okay. So maybe I have to do it like this. Okay. So let me do it again. Okay. So I have. Okay, so I have this one here. Okay, so this I do like this, and this I do like this. Okay. Okay, so I somehow double these things a little bit, and the weights which I'm giving is very special. It's 1 alpha. So there's a 1 parameter family of determinantal parameters. It's 1, 1, 1 alpha. So these things together give 1 plus alpha. So this is a sort of what you want in order to make it exactly like the domain wall boundary condition, and this is 1. Okay. And now the claim is that if you now do exactly what I'm saying, and if you look at this, I mean, then you will find that it sort of satisfies sort of particular. So you will have, you see, I mean. If you have a line ensemble, you want to have it not just a line ensemble, but you want to have it particular way, so it actually becomes determinantal. And this trick sort of you have to do in order to be sure sort of on a particular theorem which tells you under what condition, if I sort of write down for you a non-intersecting line ensemble, it is actually determinantal. So this actually, if you really want to know about it, I mean there's a paper which I once wrote with Patrick Ferrari. And this construction is sort of, completely explained. Anyway, so this with this construction, these lines, and with this special choice of parameters, it is actually determinantal. And so I just want to show you, where we are in the bulk phase diagram. So I look at the symmetric case, which is omega 1 equal omega 2 equal A. I mean omega 3 equal omega 4 equal B, and omega 5, I hope that's correct, it's equal omega 6 equals to C, and then I normalize by C. And what I'm plotting is the phase diagram of this system as a function of so this is just a bulk phase diagram with periodic boundary conditions. Okay, so this is A over C, and this is B over C. And then there will be sort of 4 domains. Okay, so this region is disordered. Here you have ferromagnetic ordering. Here you have ferromagnetic ordering, and here you have the anti-ferromagnetic. Okay, anti-ferro. Now, here there also happened something interesting, but it's beyond what I can say at the moment. I mean, so it's different. I mean, it's also KPC, but it's more complicated, and it looks different than what I'm set here with. So just forget about this regime. Here it's perfectly ordered. So basically, what this circle sort of degenerates. I mean, either you get a line which separates these halves, or you get the line which is sort of sort of oriented, along the anti-diagonal. So here, I mean, you have this phenomena, but it's completely degenerate. I mean, so that's not interesting. So whenever you have in disordered D, you have KPC edge fluctuations. That's the conjecture, edge fluctuations. And the line along which you can this actually check is a line which is sort of defined by this parameter alpha, and which in these units is sort of, the free fermion line of the 6-vertex model, which is again a semicircle and which looks like this. Okay, so on this line we know the result. Well, unless Philip tells me that in the meantime he solved this problem also in the other one, but at least to my knowledge, I mean, along this line, I mean, that sort of actually it's really solid proof. But and including also the fluctuations of this, the line fluctuations itself, not only at one point, but everything else in this disorder domain. I mean, this sort of stands as a conjecture. Yes. Ah. Okay. Well, no, it's a conjecture. I mean, could very well be. I would be very, happy to. Yeah, sure. Okay. So now I want to. This was sort of this part, and now I want to sort of switch to. I mean, still 6-vertex model, but I want to switch to a very different part of the phase diagram. A over C and B over C. And C are these weights. I mean, so the 1 and 2 are equal, 3 and 4 are equal, and 5 and 6 are equal. Okay. All right. Now I'm still 6-vertex model, but I want to look at a very different part of the phase diagram. So this was domain wall boundary conditions, and now I want to look at the stationary case. Okay. Now you should imagine that. I do this tiling with periodic boundary conditions. I sort of go to the infinite volume limit, and then I want to study what I get. Okay, and so now I want to be in a regime which is called delta larger than 0, which is sort of ferroelectric phase. Okay, and now I want to look at the free energy. And I'll think of this sort of elastic picture. I mean, so there will be sort of like bulk parameters, but then there will sort of be like two magnetic fields, and these two magnetic fields basically tell you how I can tilt the surface. So what I in my picture I will disregard sort of the bulk parameters. I mean, they are sort of they're sort of somehow. I mean, they are constrained by satisfying this condition. But then there are sort of two electric fields really. But anyway, there are two chemical potentials which allow me to tilt the surface in these two directions. And so now I want to plot the free energy as a function of these two parameters. So this is the H1 and the H2. Right? I mean, so I need two parameters because it's a normal, and I need two numbers to tell you now in which way this surface is actually oriented. Now, of course, the surface, because I'm looking stationary, is now on average perfectly flat. So it's really like this paper, but there's still a macroscopic tilt, which I can enforce by taking my infinite volume limit with sort of suited boundary conditions, or if I add explicitly into my partition function this kind of chemical potentials which corresponds to these values. Okay, so what one finds is actually that there is a line which looks like this. Okay, so now so out in this direction I have my surface free energy. Okay, so now I'm sort of just trying to tell you. So here there's a line. So this free energy looks like a roof of a building. I mean, so here is sort of just very sharp, and then this roof down here has sort of something which sort of so here the roof is flat. And here it's sort of somewhat rounded, if you want so. Okay, and will look like the same over here. And so flat means that the free energy is really just a linear function. And in fact, I mean, there the system is completely frozen. I mean, you will see the configuration omega 1, and you see the configuration omega 2 here. Okay, and you know it's completely frozen. Therefore, it's just a linear function. Doesn't has no smooth dependence. But then there are this part where I see some rounded behavior, and now there's very one special point in this in this phase diagram, which is usually called the conical point. So there's this point here, which is called the conical point. Okay. And now I'm going to sit myself exactly at the conical point. Okay, so in fact this will still leave me a few parameters, but it's not so important. I mean, so let me sit exactly at the conical point. Okay. And so the claim is that 6 vertex at the conical point is equivalent to stationary. Okay. So this actually, in this case, it's even a proof. I will give you an argument so that you believe it immediately. But okay. All right. So let me try to explain this a little bit. So in particular, I mean, what one knows is that if I'm going to compute the 2-point function, of the 6 vertex model exactly at the conical point, it will be exactly the same as the 2-point function of the stationary KPC equation, right? I mean, on large scales, I mean, there's always, of course, universality involved. So now let me sort of convince you why this is true. And one way to see this is that, so let's see, I have to think a little bit here what I should tell you. Okay, I didn't put the most important thing. Anyway, so, okay, I think that's good enough. So, the way you can see this is that you consider the diagonal transfer matrix. Okay. Which at the conical point has some very special properties, as you will see in a second. And the way how I do this this diagonal transfer matrix is that so here's my lattice. So this is the I, that's the J coordinate, and so here you have my underlying lattice, and now I'm matching that along these lines I do my transfer, right? And well, what do I transfer? Well, I mean, I introduce the usual eta HJ, which is sort of 1 if there's a line, and 0 if there's no line. And now I want to sort of understand, how if I put it already in the infinite volume limit, I want to know in which way I maybe could possibly construct the statistics of the 6 vertex model at the conical point in the infinite volume limit. Okay. And so let me, since time is short, let me just give you the rules of the updating, and you have to sort of do a little bit of thinking and drawing. I mean, to confirm what I'm trying to say, right? I mean, so let me just sort of give you the rules. Okay. So you go from line to line, and then let me draw this line here sort of separately, and draw it in such a way that you can most easily see the updates. I mean, so here there will be, of course, it's discrete, right? And the same thing will be up here. And the way you should think about it is that that the actual tiles, I mean, you see now I've sort of shifted this by 90 degrees. I mean, so the actual tiles are sitting something like, they are sitting something like this in this picture. And if I start trying to draw the tiles, I mean, presumably, I will get mixed up myself and will mix up yourself even more. But I just confirm that if you sit down and or look it up, I mean, then you will see that that's sort of correct what I'm saying. Okay, now the idea is that you first start blocking the system in 2 blocks. Okay. And basically what I have to do is I have to tell you how I do this update. Now, of course, I will have 4 possible configurations here, and there will be sort of the corresponding 4 possible configurations sort of after one time step. So time is, let's say, running for me upwards in this case. And so I will tell you in a second. But I do this sort of independently for each block. And now to get something interesting, and that of course, just comes here because I'm looking diagonal. I mean, then, things are interlaced already in the proper way. So, there's one tile which is sitting here, but then the next tile will be sit over here. So if I do now the next time set, I will do exactly the same rules, but now the blocking will go shifted by one lattice unit, right? I mean, so I will make blocks like this. And then if I do the next one, I will do the update exactly according to the same rule. So if I tell you the update here, I mean, then you know how to go. And the assertion is that if I do this, if I start the update sort of with the correct sort of initial distribution, which is sort of stationary under this update, then, well, it's not really, it's stationary under 2 updates actually. It's sort of 2 periodic. Then, and if I do this sort of forward in time, backward in time, this will be exactly identical to the 6 vertex model. Okay, and so what is the update? Well, it's sort of pretty easy. I mean, so there are lots of updates which you don't have much choice. I mean, so okay, so I just go to 0 0 again, and then I go to 1 1 again, and then I go to 1 0 again. I don't do anything, right? I mean, this is what I do. Okay, and so of course, this you do with probability p, but here I don't do it with a full probability. I do it with probability 1 minus p. So there are two parameters actually. It's a little bit surprising because it looks, as if I would be sort of, if I fix all these other things, I would be just at a single point. But if you do the counting correctly, I mean, you find that the number of parameters comes exactly right. So 1 minus q and 0 is less than p, q less than 1. So these are 2 independent parameters. Okay. And now the real update sort of corresponds to a jump. I mean, so I will have first of all the rule that the 1 0 goes to 0 1, and I do this with probability p, and then the 0 1 goes to 1 0, and this I do with probability q. And now you see that that's very special of this conical point. Now you see that the probabilities just add up. I mean, if I sit here, and I ask you, what I'm going to see, then I will see these various possibilities. And then I ask, what is the probability? Well, they have sort of various probabilities, but if I sum over all probabilities, as you can see, I mean, they just add up to 1, right? I mean, every possibility. You see, if I have a 1 0 over here, then I can either stay with probability 1 minus p, or, I jump with probability p. So it adds up to 1. I mean, if I have 0 0, then of course it must be 0 0 up here. That also has probability 1. Okay? So it's a simple Markov chain. It's an infinite state space, but it's a Markov chain. Now, I hope you're not too surprised. You see, if I do it like this, it looks very much like TARSEP or these models. I mean, any one of these stochastic particle systems which you sort of, which are basically sort of like the gradient of the height. I mean, it's just, of course, it's not exactly the same. I mean, you have 2 parameters, and you do discrete in time. You sort of, but I mean, somehow probabilistically, you would think that I mean, if I know it for something like the TARSEP, it cannot be much different for such kind of a Markov chain. Now, I mean, these are nice words, and you should believe them because, I mean, otherwise, I mean, we don't really know how to do physics if we sort of worry about already, such kind of sort of fairly obvious things. But of course, actually proving things is sort of very difficult. I mean, this was open for a long time, and there's a fairly young fellow at Harvard, which is Agarwal, his name. You can look at I think he posted his paper in 2016, and so he studies this in great detail, and he first shows that I mean, the 6 vertex model and these things are actually really the same, and then this is, as I said, I mean, it's much more difficult than for instance the P&G model, but he has sort of somewhat novel methods which are sort of actually quite recent. But anyway, I mean, so at the end of the day, I mean, for that very particular Markov chain, he can prove that the corresponding height fluctuations are actually Tracy-Widom-like. Well, they're not Tracy-Widom-like because we're in the stationary regime, but he can prove that they are sort of okay. So he proves that I mean that this Markov chain, or if you want to, that six vertex model. So for the conical point case, conical point. Basically, what he proves is that the stationary correlations. I mean, let's say the stationary 2-point function is the same as the stationary 2-point function. Now we don't know how to compute it for too many models, but I mean it's the same as the stationary 2-point function for the PNG, where we know how to compute that for the RCEP. TARCEP also for the KPC equation, we know how to compute that. And that's sort of more or less it. I mean, we don't know how to do it for very many models, but they are sufficiently, in particular when you look at PNG, KPC and this model, they are sufficiently distinct. And on the large scale, you always find exactly the same stationary distribution. Okay, so I have no time to really go into more details. I don't know how many minutes are you still granting me? Yeah. 10. Okay, so that's very good. So I think this is sort of. I think I have just one page which I still want to explain to you. So maybe I can do this in these 10 minutes, because I want to sort of mention yet some other tiling. Okay, so this was the six vertex model, and now I want to sort of mention some other tiling. Well, let's do a clean blackboard, okay? So here will be even more pictures and just reporting on something which I think is sort of useful to be known. And so this nowadays sort of goes like so this chapter 10. So this goes under lozenge tilings. And I mean, if for this purpose and because of the time, I will in fact never try to draw any tiling. I just want to just explain the sort of the physical motivation and once I've explained this, I mean you will see immediately why people call it lozenge tilings. Okay. So let's look again at the Ising model. I mean temperature 0, and I want to use the lattice gas language. So I think of sites or cubes either being occupied by a particle or not, and then so at 0 temperature I'm thinking sort of more like it's really more like a crystal, right? I mean, and let me first just so you can understand the idea. I mean, let me first do dimension 2, and let me imagine that I look here at a quadrant, and let me imagine that I'm at t equals 0, everything is filled, and so I have everywhere I have sort of my atom sitting here, and this is a ground state energy configuration. There are no fluctuations whatsoever, and that's the end of the story, right? Okay, but now of course you could say, I mean, somewhere it has, of course, somewhere it has to be finite. I mean, I could say, well, look, I mean, maybe the number of particles which I had at my disposal, I mean, they're just not exactly the numbers which fit into a big square, and therefore let me sort of remove n can be arbitrary, n atoms. At the moment, I mean, it's arbitrary. I mean, so well, no, let's remove exactly n atoms at the moment, okay? And now let's look at minimal energy configurations in this situation where I have n atoms removed. Well, that's easy to describe. I mean, so okay. I mean, I can sort of do something stupid. I mean, I can just take, an atom sort of, right in the middle. But I want to remove n atoms in such a way that the cost of energy is sort of is sort of minimal, right? I mean, with minimal energy cost. Okay, and that's not such a difficult problem. I mean, of course, what I'm going to have will be something like this. So here I put some height function. So the new thing which I will get is sort of like a line, maybe like this. Okay, I mean this area, of course, are the n atoms which are removed, and out here I have my crystal, let's say, right? But now you see that there are many configurations which I can remove, and so now, of course, I can ask, what about the fluctuations of? The language will be that, you know, this is totally flat. I call this a facet, and this will be sort of like the boundary of the facet. So there will be, you know, lots of fluctuations in this boundary, and so you can ask yourself, if I take sort of a suitable large n limit, I mean, what will this boundary look like? Well, that's something which is a nice exercise which I recommend to everybody. I mean, if you look on the large scale limit, I mean, actually you will find a limiting function, and this limiting function is, if I call this x and if I call this y, then it's e to the minus x plus e to the minus y equal to 1. That's a nice exercise in equilibrium statistical mechanics, and of course you can also study, you know, the fluctuations of this boundary, and so this goes all the way to infinity here. There are fluctuations, and you will find that the fluctuations are actually Gaussian. So now I want to do the same thing, but I want to now do the more physical dimension of actually 3. Okay, so the picture is just the same. You know, I just have some extra coordinate, and now let me sort of define the statistical mechanics problem a little bit more precisely. You see, what I do is here I have a height function which is decreasing, okay, and then the statistical mechanics is just saying that, you know, take a uniform distribution, because we're at t equals 0, the uniform distribution of overall height functions which are decreasing, and which have an area under function which is exactly given by n. Right? I mean, that's the statistical mechanism. So now if I do this three-dimensional problem, you know, it will look sort of more or less similar. I mean, so maybe I draw it like this from the front. I mean, so this is my three-dimensional object. So originally it's a cube, but then I remove n atoms, and then of course it will be at the corner, you know, with minimal energy, so it will be at the corner, which I can remove, and then actually the picture which you're going to see is sort of something which is, you know, on that part I will see something which is perfectly flat. I mean, that's a facet. And also something over here. But then, you know, given these lines, I have sort of like a rounded piece where I will have a lot of disorder. I mean, so this is the disordered region. And so the lozenge tiling comes that if you do a projection along the diagonal, I mean, if you do a 1-1-1 projection, then you can view this also as a problem of tiling particular domains or with particular boundary conditions with lozenges in the plane. Okay, so it's really isomorphic. Anyway, so let me just use here the more intuitive sort of crystal thing. So what is the problem? Well, I have a height function. So I have a height h, I mean, which is positive, and hij must be less or equal to h plus 1 j, and the same thing for the other coordinate. It must be decreasing in both coordinates, and of course I want to have the area under these things well, up to infinity. Of course the height function has to go to 0, otherwise, you know, it could not have and of course, you know, the n should be large. And then I take uniform distribution. So this is the statistical mechanics problem, okay, which corresponds exactly to what I've been saying. Of course, if I take a true cube, I mean, then, you know, I will have the 8 corners, and then at each one of these corners I have to make this discussion. So I'm just looking at one corner, and then you will see this thing, okay? Okay. Now let's think about this for a little while. Okay, so now what I'm so here is the h direction, right? And now I get this line. So I get the height lines. Just what we had for the 6 vertex model. I mean, so, you know, maybe I have something like this, and then maybe something like this. This is 0. This is 1. This is 2. Right? I mean, so I can think of I mean, you know, because it's decreasing both coordinates, you know, I can think of, so now you think, you know, I see already my non-intersecting line ensemble. I mean, that's of course true, but it's okay, but the real line ensemble which you want to study is sort of slightly different. And so the idea is to rather having the height lines, I'm doing the gradient lines. I mean, so I go from here all the way up to here, and then I do the next one. Okay, go up here, etc. Okay, and now I'm doing a recording of the height along these lines. And so this is now j. I mean, j goes now from minus infinity to plus infinity. And if I take this first one, I mean, you know, this will be a fairly large height. I mean, so now you know, because out here it's all zero. I mean, so if I would draw the heights over here, you know, I mean, they are sort of would be completely overlapping. I mean, so I do the gradient, and then I do a plus shift. I mean, these are the gradient lines plus shift by 1. Okay, and so you know, if I'm out here, I mean, then you know, I mean, let's say the one which I do out here, which is all zero, it's shifted downwards. I mean, so there will be a line here, there will be a line here, there will be a line here. I mean, this just corresponds to this totally flat piece. Okay, and now I can do this one. I mean, so this would be sort of like the top line. I mean, so I go here, then go here. I mean, so this will be sort of something like maybe coming up. I mean, it has to go up, right? I mean, so it comes up, goes up. And then, of course, here it must go down, it must go down. Okay. And then there will be a next one. Okay, etc. Okay. So this is the non-intersecting line ensemble which I want to study. Okay, it's just, and you see this one here, I mean, maybe from here you cannot see it so easily, but this one here will be the facet. So in this picture will be this facet, which is given by this line. So this one is here is the facet edge. This facet edge, I mean, this is what I want to say, right? So you see, it's the same picture. I mean, we have sort of an ensemble of lines. It's the top line which gives us sort of the quantity which I want to study. I want to study how the facet edge is actually fluctuating, of course, of thermal fluctuations. Okay, and as no surprise, I mean, I have to do one thing, namely I have to, rather than working canonical, I have to go to the grand canonical description. So, you know, rather than looking at this, I have to look at e to the minus beta, the summation ij, hij. And when you do this weight, I mean, miraculously, it so happens that the lines are determinantal. Now, in this case, the determinantal process sort of has rather different sort of features, because you see, I mean, it's one-sided. Here I do jumps always up, and then here I do them always down. Before, you know, it was doing like a symmetric walk. I can also have jumps which you know, they can be on top of each other. I mean, there's no, you know, I draw it as if it would be height 1, but that's misleading. I mean, you know, if you think about stacking the cubes here, of course I can stack several over them and continue. I mean, you know, the height difference were never constrained to be equal to 1. I mean, you know, this could go down by I don't know, 10 units, for instance. I mean, that's perfectly fine. So these heights actually are not equal to 1, but they have another nice property, namely they have sort of like so the height under these things, the height differences have geometric weights. So it's some parameter which depends where I'm sitting, geometric weights. Anyway, so at the end of the day, we have another determinant line ensemble, which, you know, very closely looks like the one which I showed you for the 6 vertex and which I showed you for the PNG. We analyze this thing, and what you can show at the end is that indeed, I mean, you know, you find that really physical systems, I mean, but the conclusion of this thing is that conclusion. So crystal facet. So this means, you know, first of all, physically, you know, I really need a facet, but this facet will stop somewhere. Crystal facet edges have equilibrium statistical fluctuations, which are in the KPC class. Okay, so that's a good point to stop. Thank you very much for listening. And I'm sorry that, the last chapter was really a little bit much compressed. I would have loved to tell you more, but all good things have to end sometimes. So thank you very much.